Thank you so much for coming. I spent 4 of the most formative years of my life as a student here in Berkeley, and it's always very emotional for me to come back. So I called the talk Black Holes, Firewalls, and the Limits of Quantum Computers. Black holes and firewalls are mostly just to get you in the building. I'll say something about them at the end. Quantum computers, when I do a Google image search for quantum computer, that's one of the first things that comes up. It'll become clear in this talk that I'm not an engineer. I'm a theorist, but I don't think that's what they look like. I've been in enough lab tours that they look a lot messier than that. Okay, so and by the way, you can find the slides and a bunch of sort of articles that from technical to popular about many of the things I'll be talking about on my homepage. Okay, so my starting point here is not about quantum mechanics. It's just about the limits of technology. Okay, there are certain things that would be awesome to have, but yet we never seem to see them. First of all, warp drive. Where is it? I've been waiting since I was a kid. Okay. Secondly, the perpetual motion machine. The only real solution to our energy problems. Okay. And then thirdly is what I'll call the Uber computer. Okay, and this is a machine that doesn't necessarily tell you the meaning of life or anything like that. But it immediately answers any well-posed mathematical question that you put to it. Okay, so here we see it saying, gold box conjecture true, next question. Just saying, yes, every even number 4 or greater is the sum of 2 prime numbers, right? I think some people have the impression that this is already what computers are. Okay, but one of the most basic things we teach in the theory of computing is that even the fastest computers today, are powerless against certain kinds of problems. They have limitations. There are certain problems like the halting problem, to tell whether a given program will ever stop running, which are proven to be unsolvable, in that case by Alan Turing in the 1930s. There are other problems that computers can solve, but only, we think, by using astronomical amounts of time. Okay, so now I'd like to make the observation that in the first 2 of these cases, we can say something about why these technologies are not around, which is more illuminating than just, the engineers ran out of money before they could build it, or something like that. Okay, we can connect this to fundamental principles of physics. Okay, in the case of warp drive, those principles are those of special relativity, which tell us that if you could send a signal faster than light, then in someone's frame of reference, you're sending that signal backwards in time. Okay, and then you've got to worry about, what happens if you go back in time and you kill your grandfather, therefore you're never born, but therefore no one kills your grandfather, therefore you are born, and no one wants to worry about that stuff. Okay, so in the case of the perpetual motion machine, of course what rules it out is the increase of entropy, the second law of thermodynamics. Okay, but what about the third case? Are there principles of physics that tell us what computations we can and can't perform? So that question is sort of the starting point for me. Okay, what does physics tell us about the limits of computers? And if we understand those limits, can they then feed back and tell us anything new about physics? Okay, so I guess I'll take 5 minutes to give you a crash course on some of the basic concepts of the theory of computing. That's all I should need for this talk. Okay, computer scientists like to take sort of any concept or notion of what a computer could be and associate to it some inscrutable sequence of capital letters. Okay, so the most these gives us things called complexity classes, which are sort of one of the most basic objects that we study. Okay, and maybe the sort of central complexity class is called P for polynomial time. Okay, and you can think of it informally as the class of all the problems that are solvable efficiently by a standard digital computer like the one in your pocket. Okay, formally you would say a Turing machine, which is the mathematical model of what a computer is, laid down by Alan Turing in 1936. But today it's it's easier just to say the thing that's in your pocket. Okay, so what do we mean by efficiently? Well, we have a sort of rough and ready criterion for that it means solvable using a number of steps that grows at most like the size of a problem instance raised to some fixed power. Okay, like the size of the problem squared, the size of the problem cubed. Okay, and by the way, by a problem, we mean sort of an infinite collection of, let's say, yes or no questions. Okay, so here would be an example, right? So this is we could consider what's called the connectivity problem, okay, where I give you a description, a map described somehow as a string of bits, and I ask you, is a given point connected to a given other one? Okay, an instance of this problem, which confronted me this past week, is it mathematically possible to get between Berkeley and Palo Alto? What if there's traffic? Okay, so this is a famous example of a problem that is solvable in the class P. In fact, there is a linear time algorithm, which will get invoked anytime you use Google Maps, basically. Okay, so so this is something that is that we consider efficiently solvable. Same with multiplying numbers. Same with same with sorting, and most of the other things that a computer would do on a day-to-day basis. Okay, and and people object to the definition, by the way, because if you had an algorithm that took the problem size raised to the million power time, well, that's formally polynomial, but you wouldn't want to run that for any problem size larger than 1. Okay, but in practice that tends not to happen. So so between friends we like to say polynomial means efficient, and if there are exceptions to that, then we deal with them when they come. Okay, so so then the second important class is called NP, non-deterministic polynomial time. And this is the class of problems for which, well, maybe they're not solvable by an efficient algorithm, but at least, if there is a solution, then that solution can be efficiently checked. It can be recognized when you're shown it. Okay? So, well, one of the most famous examples of an NP problem is factoring numbers. Okay? So, if I want to phrase this as a yes or no question, I could give you a large number, like that one there, and say, does it have a prime factor that ends in 7? Okay. Well, has anyone solved it yet? Okay. So I think in this case the answer is yes, but I made this slide a long time ago, and if the answer is no, I'm not sure. Well, so the thing to notice is that if someone has solved this problem, then it's pretty easy, at least with a computer, to check their solution. Okay, as it turns out, this is not quite obvious, but there are very fast algorithms that can tell you whether a number is composite or prime. Okay, if it's composite, they tell you nothing about what the divisors are. Okay, but they do tell you if it's prime or not. So you could give someone the divisors of this number. A person could use their computer, multiply them, That's an easy operation. Check that, they do multiply to this thing, and also check that they're prime, and then just check whether one of them ends in 7. Okay, but if someone didn't tell you, what the divisors were, well, you might spend quite a bit of time looking for them, right? And, in fact, many of you might know that the security of, essentially all the cryptography that we use on the internet today is based on the belief that factoring and a few closely related problems are hard, okay, that there is not going to be any efficient algorithm to solve these problems. Solution is much, much easier to check than it is to find. Okay, so anytime you see a little padlock icon on your web browser or an HTTPS, right, your information, like your credit card number, is being protected by a by a cryptographic code that depends on the belief that this kind of problem is hard. Okay, we'll come back to that. Okay, so then a further crucial concept is NP hard problems. These are problems that are sort of at least as hard as any problem in NP, in the sense that if you had a magic box to solve them, then you could use that magic box to solve any other NP problem. Okay, well that's a weird definition, not clear that there's any problems like that, but there are. There's oodles of them. Okay, and then the NP complete problems are the NP hard problems, which are also themselves in NP. So those are sort of like the maximally hard problems whose solutions are still easy to check. The maximally hard NP problems. Okay, now a central discovery that, in the early 1970s that, really started, theoretical computer science as sort of its own field was the discovery, which was, which was really sort of which a central participant was the guy who introduced me just now, Karp, that not just one or two, but many, many, many hundreds of the problems that people actually care about and actually want to solve happen to fall into this NP-complete class. Okay, a famous example being the problem, I give you a map like this, and I ask not what is the shortest path, or is there a path from A to B, but just is there a path that hits each vertex, in this case, exactly once. Okay, in this case, what's the answer, anyone? Yeah, yes, it's easier to see when you color it in. Okay. Okay, so you may have heard the literally million-dollar question of this field is, whether P is equal to NP. That is, for every efficiently checkable problem, is it also efficiently solvable? Okay, this question has entered popular culture. It's been on The Simpsons, Futurama, other TV shows and movies that are not as good. It's also one of the 7 Clay problems for which you get $1 million prize for a solution, alongside the Riemann hypothesis, the Poincare conjecture, which was actually solved by Perelman, although he declined the prize, and 4 other problems. Okay, now my personal opinion is that P versus NP is actually manifestly the most important of all these problems. Okay, that it is the biggest problem in mathematics. And my argument for that is simply, well, if P were equal to NP, and if moreover the algorithm were really efficient in practice, so not n to the 1 million or something like that, well then that would answer this question. But it would also mean that we could answer the other 6 questions, because we would simply program our computer to find the answers for us. Okay, the problem, like, given a mathematical statement written in some formal language, like that of set theory, is there a formal proof of this statement with at most, a given number of symbols, like, 1 million or 1 billion? That is an NP problem. So if P were equal to NP, that would be an efficiently solvable problem. Okay, so that I hope helps to underscore the enormity of what we're asking, right? if P were equal, so I mean, this meta-mathematical importance was recognized early on by Gödel, the incompleteness guy, in a letter to John von Neumann, where in 1956. Okay, I mean, if P were equal to NP, that would also break essentially all of the cryptography that we use today. Everything except stuff like the one-time pad, which doesn't depend, or like quantum key distribution, which don't depend on mathematical assumptions. Okay, are they equal or not? I like to summarize it by saying that if we were physicists as opposed to math and CS people, we would have simply declared P not equal to NP to be a law of nature. Okay, and we would have given our, we would have said, of course, look, we tried, we looked for an algorithm, it's not there. Of course you can't solve it, right? What are you going to do? You've got, a gigantic search space, 2 to the n possibilities. Yeah, maybe you can cut it down a little here or there by being clever, but, polynomial, come on, right? And, we would have given ourselves Nobel Prizes for that discovery. Okay, and and by the way, if someone later proved that actually P equals NP, well, we just would have given ourselves more Nobel Prizes for the law's overthrow. Okay, so there are sort of one thing you learn in quantum computing. It's an interdisciplinary field. And different fields have different terminology. So what the physicists call a law, we call a conjecture. Okay. So but even if we accept that probably, presumably, P is not equal to NP, and we hope someday to be able to prove such things, but we seem a long way from that now. One can then ask a further question. Okay, P versus NP itself, is a purely mathematical question, right? It has a, whatever's the answer, it has an answer, right? Which is totally independent of whatever the laws of physics are, right? Because, it just asks, is there this Turing machine or not, okay? So, it doesn't even make sense to ask, well, does quantum mechanics change the answer to P versus NP? No, of course it doesn't, okay? But there is then a further question you can ask, which is, well, supposing P is not equal to NP, is there any physical means at all to solve NP-complete problems efficiently? Possibly a means that would exceed, the capabilities of Turing machines, right? Because a Turing machine is just one particular mathematical idealization of what a computer is. Okay, it's not obvious that the laws of physics, restrict us to that kind of computer, right? Maybe they let us do something else. Okay, so when we ask sort of what are the ultimate limits of computers that we could actually build, well then of course we're asking a question about physics, and physics is going to enter the discussion. Okay, so the idea that the limits of what we can compute in the physical universe sort of coincide with the limits of a Turing machine is sometimes called the Church-Turing thesis. Okay, although it's not clear that Church or Turing themselves ever said that or believed it, but it's sort of like well, if they didn't say it, they should have. Okay, but then you could make an even stronger belief, which is that whatever is efficiently computable in the physical world should be efficiently computable, in the sense of polynomial time by a Turing machine. Okay, but now we're really sticking our necks out, and we're really making a falsifiable empirical claim about nature, right? Nature doesn't have to listen to us, or if we even if we enunciate it as a principle, right? Nature might go and ignore that principle. Okay, so it behooves us to ask, what is there in nature that could conceivably challenge that extended Church-Turing thesis, right? What could a physical system look like that could possibly exceed the limits of a Turing machine? Okay, so you probably all know where this is going, given the title of the talk. But before we get to quantum computers, let's just briefly discuss a few other examples. Okay, so there's an old proposal I like, which is that you take two glass plates, you put pegs between them in whatever pattern you want, and you dip the resulting contraption into a tub of soapy water. And then you take it out, and you look at the soap bubbles that form in between the pegs. Okay, and bubbles like to sort of relax to their lowest energy state, which in this case, presumably means sort of minimizing the total length of bubble, going in between these pegs. But now, if I ask you what's the minimum total length of line segments connecting a set of points in the plane, where those line segments could also meet at intermediate points like these, well, this is called the minimum Steiner tree problem. And this is a famous example of one of those NP-hard problems. Okay, so now we're faced with a puzzle, which is basically, if this problem is NP-hard, well, then how does nature solve it? Okay, how does nature do this? And, is it possible that, a tub of soapy water does what all of our supercomputers cannot do? And that, we could, just have, soap tubs, to break all the cryptographic codes that, all of our enemies are using. Okay, so, there was a discussion of this on the internet some, years ago, and and some people said, well, there's sort of no reason for to imagine that this will always work, right? Because systems in nature like to relax to their lowest energy state. They can often be modeled as doing that, but they can get stuck. They don't always succeed. As an example, if I put a rock on a crevice on a mountainside, well, it could reach a state of lower potential energy by rolling up first and then rolling down. But it's rarely observed to do that. Okay, so so why shouldn't we imagine that the same is true here? That you would get stuck in a so-called local optimum. All right, well, so then someone else came and said, but this is just an academic computer scientist party line. You all repeat that. You pat yourselves on the back. I bet not one of you has ever tried the experiment. You have no idea what would happen. All right, well, I told you that I'm a theorist. This led me to the one foray into experimental physics in my career, where I used to take this around and do demonstrations, but it was just hell to get it through airport security. So, what I found when I tried it is that indeed, with 4 or 5 pegs or so, you usually do get the minimum Steiner tree, and it's cool to watch. You can try it at home. If you do, I recommend using plexiglass instead of glass so you don't cut your hands. Ask how I know. Okay, so. But then, if, when you scale up more, say to 6 pegs, 7 pegs, then it doesn't always find the optimal solution. In fact, sometimes you find a little cycle of bubble, which is then like a proof that it can't be minimal. Okay, so, I didn't try every possible brand of soap, but, I think, I think we have at least some circumstantial evidence that nature is not solving NP-complete problems by magic this way, right? And that may sound silly, and yet every year or so, you'll see in the popular press another headline about, biological system that solves NP-complete problems, protein folding, right? Nature just, every cell of your body solves an NP-complete problem every second by, just letting the proteins fold into their lowest energy state. Okay, I think that similar comments apply. In that case, with proteins, well, there was strong selection pressure on them, right? If one could, in principle, create an amino acid chain such that, to fold it into its lowest energy state, you would need to prove the Riemann hypothesis first, right? That this is what NP hardness means, okay? But that would be a pretty bad protein, right? It wouldn't, proteins that get selected will tend to be ones that do fold reliably. Even then, there are proteins that can misfold, get stuck in local optima. Prions, the agent of mad cow disease, are apparently an example of that. Okay, so all right, my second example is, you hear about quantum computers all the time, but why not a relativity computer? Okay, so the idea here would be quite simple. You start your computer working on some hard problem, then you leave your computer on Earth, and you board a spaceship, and you accelerate to relativistic speed. Okay, and then you decelerate, you return to Earth. Okay, back in Earth's reference frame, billions of years have now elapsed. Okay, civilization has collapsed. Actually, in our timeline, civilization probably collapses by 2019 or something. But at any rate, it's certainly collapsed. By then. Okay, but if you can. Just sort of somehow dig your computer out of the rubble and it's somehow still connected to a power source, then you can read out the answer to your hard problem. Okay, so to me, this just raises an immediate question, which is why doesn't anyone try this? I mean, if you're worried about all your friends being dead, just bring them on this spaceship with you, But, so we're asking, what is it in fundamental physics that would rule this out, that would prevent you from getting arbitrary computational speed-ups in this sort of way? So I think there's actually an interesting answer to that question, okay? And it has to do with the amount of energy that it would take to accelerate to, relativistic speed, to get this speed up. Okay, so what you can calculate is that if you wanted, say, an exponential computational speed up this way, then you would need to get exponentially close to the speed of light. Okay, but to do that would require an exponential amount of energy. Okay, so we've sort of just traded one exponential for a different one, right? And now, we're to imagine that before liftoff, you spend like exponential time just fueling up your spaceship, or something like, where do you find all this fuel? Okay, so it's an example of how very, very often you'll see proposals for these sort of hypercomputers that would exceed the limits of Turing machines, but then on analysis they're just based on taking one aspect of the laws of physics in isolation and ignoring all the other aspects. Okay, so that's a cautionary tale, right? We better not do that. Okay, a second example along the same lines is what I like to call the Zno computer. Okay, now this is simply a computer that would do its first step in 1 second, the second step in half a second, the third step in a quarter second, fourth step in an eighth second, and so on, so that after 2 seconds it would have done infinitely many steps. You could solve the halting problem that way. Okay, but so again, why doesn't anyone try that? Okay, well, in this case, then, in some sense, there are people who try this, right? There are people who overclock their microprocessor, right? They run it faster than, it's supposed to. Okay, but many of you might know the danger in doing that, which is that if you run your processor too fast, it will overheat, it'll melt. Okay, this is why computers have fans, right? But, again, we can ask, well, but what is the fundamental physical limit here? Okay, well, you can imagine trying to run a microchip faster and at a faster and faster and faster clock rate. As I want to run it faster, to do that, I will need more and more cooling. I'll start, wanting liquid nitrogen or liquid helium, as some supercomputers used to actually use. Okay, and and the more cooling I need, the more energy that will cost. You see, once again, energy. Okay, and then once my computer is running fast enough, I might as well just forget about the cooling system and talk about the energy that's inherent in the computation itself. Okay, now, as far as current physics can say, the fundamental limit here seems to occur if you were to run a computation at about 10 to the 43 hertz. Okay, it's 10 to the 43 operations per second, 1 step per Planck time. Okay, now you could think of a toy model of such a computer as just a photon that's bouncing back and forth between two mirrors to count off time steps. When the mirrors would be 1 Planck length apart, that it's 10 to the minus 33 centimeters. Okay, now what's the problem with a computer that runs that fast? Well, the problem is by Planck's relation, E equals hv. Okay, such a photon would have so much energy concentrated in so small of a region that it would exceed what's called its Schwarzschild radius. Okay, that's just a fancy way of saying that your computer collapses to a black hole. Okay, which I've always liked as nature's way of telling you not to try something. Okay. Okay, but what about quantum computing? I mean, we knew it was coming at some point. those are supposed to be spin 1/2 particles, although I don't think that's actually what they look like. All right. So in order to tell you, I mean, quantum computing, like when you first hear about it, it sounds, roughly as crazy as those other things that I just talked about. Okay, and yet we know that there are experimental groups all over the world which are currently, working very hard and, spending significant money to try to actually build these things. Okay, so, what's the difference? Well, the quantum computers are machines that would be do computation in a fundamentally different way by exploiting the rules of quantum mechanics. Okay, which is something that's has been sort of the basic operating system for physics since the 1920s. The thing that everything else sort of runs on as application programs. Okay, except for, general relativity, there's some technical problems porting it to the OS. Okay, but what is this operating system, right? And like, what is there that's in it of sort of comparable enormity to the church, to the extended Church-Turing thesis, that the one could actually challenge the other? Okay, so I have to spend a couple slides telling you about what does quantum mechanics say. You might think that would take more than a couple slides. I mean, physicists, I think over generations, we succeeded in convincing people that quantum mechanics is somehow complicated or hard. And it's true that if you want to know, the ground states of, interesting molecules and so forth, yeah, that's complicated. Okay, but not being a physicist and not being bound by their rules, I can let you in on a secret, which is that quantum mechanics is actually incredibly simple once you take the physics out of it. Okay, now, the way that I think of quantum mechanics is that it's a certain generalization of the rules of probability themselves. Okay, so probability, you could talk about, well, a 30% chance that wildfires will consume the Bay Area or whatever, but you would never talk about a negative 30% chance, right? Let alone an I%, square root of -1% chance. Okay, that would just be nonsense. Okay, but quantum mechanics fundamentally is a generalization of the rules of probability, where to each possible way that things could be, or that we could find things on looking at them, we assign a number called an amplitude. Okay, and amplitudes are a little like probabilities. In fact, we use them to calculate the probability that we'll see a system in one state or another when we do look at it. Okay, but these amplitudes are not themselves probabilities. They can be positive or negative, and in fact, they can even be complex numbers. Okay, so Richard Feynman used to say that everything in quantum mechanics just boils down to one experiment, the double slit experiment. So we might as well talk about it. The double slit experiment is the thing where I take photons, I shoot them one by one at a screen with two slits in it, and I look at where they end up on a second screen. And and where they end up is random, right? With the same initial conditions. Photon can sometimes land one spot and sometimes another. And people go on and on about, well, this is God playing dice, Einstein couldn't accept it, blah, blah. That is not the strange part about quantum mechanics, right? If it was just probability, who cares, okay? We could, invent, 30 theories for that before breakfast. Okay, the strange part is the way that the probabilities have to be calculated, okay? Because what you find is that there are certain dark spots on the second screen where the photon never seems to appear, or almost never. Okay, and yet, if I close off one of the slits, then the photon can appear in those places. Okay, so by decreasing the number of ways for something to happen, I can increase the chance that it happens. Okay, also, if I just look at the photon to try to see which slit it's going through, then I don't see this interference pattern anymore, right? But I hasten to add, it doesn't have to be a conscious person looking at it or anything like that. If the photon is interacting in any way with its external environment, so that the information about which slit it goes through leaks out, into a recording device, into the air molecules in the room, into anything, then you don't see the interference, okay? Interference is something that photons, and other particles like to enjoy in private, okay? Okay, the way that quantum mechanics explains this is by saying that, well, the probability of an event in quantum mechanics is calculated as the squared absolute value of its amplitude. Okay, and the amplitude could be a sum of contributions, complex numbers representing the contributions from all the different ways that that thing could have happened. Okay, and so the result is that, there could be certain spots on the second screen where the photon could arrive there through the first slit with a positive amplitude, or through the second slit with a negative amplitude. Okay, and if that happens, then those two contributions can, as we say, interfere destructively and cancel each other out, with the result being that the total amplitude is 0 and the photon is never found there. Okay, I close off one of the slits, and then the amplitude is positive or it's negative, so then I can see it there. Okay, so physicists describe this by saying, that the state of the world is a vector, right? It's a vector of complex numbers. Okay, and they have this strange notation that they like to use for vectors. Okay, that's all this is, right? So the simplest type of quantum system is a bit, which could be in a 0 state or a 1 state, but because it's quantum mechanics, it can also have an amplitude to be in 0 and an amplitude to be in 1. Okay, it can be in what we call a superposition of the two states. Okay, a bit that can be in a superposition of 0 and 1, we call a quantum bit or a qubit. Okay, so the state of a qubit is written as A0 plus B1, where A and B are just complex numbers called amplitudes, and they satisfy this relation here. Okay, and this relation is sort of there to ensure that if you look at the qubit, you ask it whether it's 0 or 1, well then, it tells you that it's 0 with this probability, and it tells you that it's 1 with that probability, well then those probabilities better add up to 1. Okay, that's why that's there. So the possible states of one qubit, if we looked at real amplitudes only for simplicity, would simply define a circle. A squared plus b squared equals 1. Okay, 0 could be, we could take to be the horizontal direction. 1 we could take as the vertical direction. And then we can have any possible intermediate, like this equal superposition state of 0 plus 1 over square root of 2. Okay, now, if I take a superposition like that and I look at it, I force it to make up its mind about what it wants to be. And it sort of snaps to one possibility or the other. Okay, and by the way, whichever choice it makes, it sticks with it. Okay, so if it tells you that it's 1 and you look again, it says, what do you want from me? I'm 1. Okay? All right, so now I can start to tell you what is quantum computing. Okay, so now the key observation here is imagine I have not just 1 qubit, but 1,000 qubits or 1,000,000 qubits. Okay, physically, maybe that's like 1,000 particles that could all be, each of which could be spinning one way or spinning the opposite way. Right? It doesn't actually matter for our purposes, what physically gives rise to this qubit. Okay, it's, any quantum system that has two distinguishable states. Okay, but now the point is, if I have 1,000, say of these qubits, the rules of quantum mechanics tell me that if those qubits are interacting with each other in some arbitrary way, then to describe their state, I actually need to assign one amplitude for every possible configuration of all 1,000 of those bits. That means 2 to the 1,000 power amplitudes. Okay, so if you wanted to write them down, that's way more amplitudes than there are atoms in the observable universe. Okay, and yet quantum mechanics has been telling us for 90 years that to maintain the state of 1,000 measly particles. Nature, off to the side somewhere, has to have some scratch paper with 2 to the 1,000 complex numbers. And every time something happens to those particles, it has to cross off those numbers and replace them with a new 2 to the 1,000 numbers. Okay, that is an immense amount of work for nature to be going to, it's astounding that it took so long for this to sink in, that quantum mechanics, was always saying this. Okay, now, to be fair, chemists and physicists did, know this for a while. They knew it mostly as a practical problem. Okay, what they knew was that, if you're trying to simulate quantum mechanics on a classical computer, then the time needed for the simulation seems to increase exponentially with the number of particles that you're trying to simulate. Okay, and so, they invented all kinds of approximate methods and heuristics over the decades for getting around that problem. Nobel Prizes were awarded for some of the most important ones. In fact, a pretty decent fraction of supercomputer time today is used for this problem, the problem of trying to simulate quantum mechanics, with large numbers of interacting particles, in order to learn things about chemistry and material science and so forth. Okay, so it was not until the early 80s that a few physicists, like Richard Feynman and David Deutsch, started asking, well, why can't we turn that computational lemon into lemonade? Okay, so, if quantum systems are so hard to simulate with today's computers, then why don't we build computers that themselves take advantage of superposition and interference of amplitudes, entanglement between different qubits? Okay, of course they then faced the question, supposing we built such a computer, well, what would it be good for? Okay, now at the time, they only really had one answer to that question, which is such a computer would be good for simulating quantum mechanics. Okay, now, it sounds funny, but actually, when we do start to get practical quantum computers, I predict that quantum simulation is still the most important application that we know. Okay, it has, potential uses from, understanding reaction rates in, industrially important processes, fertilizer production, all kinds of things, designing drugs that bind to a receptor in the right way, maybe, understanding high temperature superconductivity, designing higher efficiency solar cells. Okay, and furthermore, we are, pretty confident that a quantum computer really would help for these sorts of problems, right? It's, because a general quantum simulator is exactly, this is sort of its home territory, right? But now, the surprise, the big, non-trivial discovery that was made in the 1990s is that a quantum computer can also sometimes be used to solve even classical problems faster than we know how to solve them with a classical computer. Okay, and the most famous example of that is Shor's algorithm. Okay, Shor's famous algorithm actually solves the problem of factoring an integer, which I talked about earlier, in polynomial time with a quantum computer. Okay, so what Shor showed is, and related problems like discrete logarithms, elliptic curve problems, and so forth. Okay, with the upshot being that, if you build universal quantum computers, then the assumptions that underlie modern public key cryptography are no longer true. You can break essentially all the systems that we use in practice now. Okay, this made many more people interested in quantum computing than had previously been. I should mention that there are theoretical public key crypto systems that seem to be resistant even against quantum attack, such as lattice-based crypto systems. Okay, it's just that those are not widely deployed yet. Okay, So, of course, people always ask, well, so where are we with building these things? I'm proud to report that, after some, probably a couple $1 billion of investment in this field and more than 20 years of effort, the experimentalists have succeeded in factoring 21 into 3 times 7 using Shor's algorithm with high statistical confidence. I'm optimistic that 35 is on the horizon. Scaling this up is hard. Actually, there are more impressive things that are likely to happen in a few years. This joke slide is even a little bit outdated now. Okay, but there's a huge practical problems in actually building this, which were understood from the beginning. And the central thing is the unwanted interaction between the qubits and their external environment. Okay, the phenomenon called decoherence. Okay, basically, when a quantum computation is being run, it is as if the entire universe is, or the entire rest of let's say your lab is constantly trying to peek in and see what's happening, just because of the natural, noise and interactions between the computer and the external world. Okay, but if you look in on a quantum computer prematurely, well, I'm told that it's like baking a souffle, right? You open the oven before it's ready, the thing collapses. Okay, same with quantum states, right? To get a quantum computation to work, you would need to have the qubits incredibly well isolated from their external environment, but then at the same time interacting with each other. And not only doing that, but doing it in a very precisely prescribed way. Okay, so that's so hard that there were a good number of physicists in the 90s who said this can never happen. Okay, this is really impossible. A huge discovery that changed most people's minds was called quantum fault tolerance, which told us that we don't actually have to get the decoherence down to 0. We merely have to make it very small. And then there are very clever error-correcting codes that can take care of the rest. Okay, so qubits are sort of just now, or just like a few years ago, have gotten good enough to apply these error-correcting codes when you look at just a few of them in isolation. Okay, the problem is as I try to scale up and have lots and lots of qubits, then the noise rate goes back up because of interactions between the qubits. Okay, but people are working on it, and Google right now has a 22 qubit system, which seems to be working pretty well. They say that within a year they plan to upgrade that to 49 qubits. Okay, when I heard John Martinez of Google say that, I asked him to clarify if he meant the calendar year or the academic year. He said the calendar year. But it will take a lot longer to test it and calibrate it and so on. He said, by December 31st, we'll have something. I don't tell you it will work. Okay, okay, but now, a crucial point to understand, okay, is that the factoring problem is neither known nor believed to be one of these NP-complete ones. Okay, there are excellent theoretical reasons why it should not be NP-complete. Okay, and if you read almost any popular article that's ever been written on this subject, right, it will say something about it that sounds really good and it's totally wrong. Okay, it will say, look, the way a quantum computer works is just that it tries every possible answer in a different parallel universe. It's like, yeah, well, journalists love that because, it's like, yeah, anyone can understand why that would make it faster. Okay, but then, the puzzle is, well, if it's that simple, then, why did it take people all these decades to figure it out? Okay, so the resolution is that with a quantum computer, it is easy to create a superposition over all the possible solutions to your problem, right? That you can do very easily. But for it to be useful, well, at some point you've got to measure the thing. You've got to get an answer out. Okay, and if I just take an equal superposition over all answers and I measure it, not having done anything else, then the rules of quantum mechanics say that all I'm going to get out will be a random answer. Okay? And if I just wanted a random answer, well, I could have picked one myself with a lot less trouble. Okay, so for that reason, the entire hope of getting a speed advantage from a quantum computer is to rely on the way that these amplitudes behave differently from ordinary probabilities. And in particular, the fact that being complex numbers, they can interfere with each other. Okay, so the idea with every quantum algorithm is to choreograph things in such a way that for each wrong answer, some of the paths leading there have positive amplitudes and others have negative amplitudes. So on the whole, they cancel each other out. Whereas the paths that lead to the right answer should all be in phase with each other, say all positive or all negative. If I can arrange that, then when I measure, I'll see the right answer with a good probability, which, even if I have a 70% chance of getting the right answer, that's great. Just run it several times, take the majority vote. Okay, so a huge question that people asked at the beginning of this field was, well, could there be an efficient quantum algorithm to solve not merely factoring, but all the NP problems, right? Or to solve the NP complete problems? Okay, well, I hope no one will be shocked if I reveal that the answer is we don't know. Okay, can we prove that quantum computers can't solve these problems? Well, of course we can't prove that, because we can't even prove that classical computers can't do it. Okay, that's the P versus NP problem. Okay, but what we can say is that at the least, if there were a fast quantum algorithm to solve the NP complete problems, then it would have to look totally different from Shor's algorithm or from any of the other quantum algorithms that we know. Okay, so quantum speedups seem to, be more specialized. This whole thing of choreographing the interference pattern, right? It works for problems that have a special kind of structure to them. In the case of factoring, Shor really took heavy advantage of the sort of number theory and group theory structure in the problem to sort of choreograph a set of operations which we call the quantum Fourier transform that gives you the right kind of interference pattern. We don't know how to do that for NP complete problems. Okay, and in fact, we have an important result about it. So my advisor at Berkeley, Umesh Vazirani, along with Bennett, Bernstein, and Brassard, proved in the 90s that if I just imagine, say, an abstract space of 2 to the n possible solutions, and if the only thing I knew how to do was, for each solution, just check whether it's valid or not valid, right? And I'm searching for a valid solution, okay? Call this black box search, right? Well then, with a classical computer, it's pretty obvious that, well, I'm going to have to open about 2 to the n boxes to find the solution, right? What else am I going to do, right? But now imagine that I can open many different boxes in superposition, okay? So with some amplitude, I can open the first box. With some other amplitude, I can open the second box, and so on. And then I get a superposition of answers. Then I can, transform that state some more. I can make another superposed query to the boxes. Okay, in that case, there is an amazing algorithm called Grover's algorithm, which lets me find a solution with only about the square root of the number of steps that I would have needed classically. Okay, so in this case, that means 2 to the n over 2 steps. Okay, but what Bennett et al. Proved, actually they proved it before Grover's algorithm was even known to exist, okay, is that that's the best you can do. Okay, so even with a quantum computer, okay, yeah, well, instead of 2 to the 1,000 steps, you can do it with 2 to the 500 steps, and that's awesome, but 2 to the 500 is still a big number. Right? You're not turning an exponential into a polynomial. You're somewhat expanding the size of the problems that you could handle. Okay, so as far as we can see that this may be like the best kind of quantum speedup that you can plausibly hope for solving NP complete problems with a quantum computer. Okay, but we still don't know, right? What we do know is that if there is a fast quantum algorithm to solve NP complete problems, which again would be like the holy grail of computer science, and 500 times more important than than merely factoring and those things. Okay, well then somehow it would have to exploit the structure of the problems. just as a classical algorithm would have to. Okay, so then the question becomes, well, are there any quantum algorithms out there that would try to exploit the structure of NP-complete problems? So there is one very famous and important one, which is called the adiabatic algorithm, okay, proposed by Ed Farhi, my other former colleagues at MIT, 17 years ago. And I don't want to go into the details of how this algorithm works, but if you've seen like local search methods, things that just sort of start at some random place and makes a bunch of local improvements, do some hill climbing, it's basically, it's basically like a quantum version of local search, a quantum analog of simulated annealing in particular. Okay, so now these are not algorithms, that typically we can prove will work, but you can try them out and see what happens. Okay, and some of you might know that there is a company which was founded, just around trying to build special purpose devices to run a sort of noisy version of this quantum adiabatic algorithm. Okay, the company's called D-Wave. They were on the cover of Time magazine, and they've gotten a huge amount of attention for it. They actually have sold a few of these devices. One to Google, one to Lockheed Martin, I think a couple of others. Their latest model has about 2,000 qubits, superconducting qubits, right? And you may wonder, well, why have I been talking about, 20 qubits or 50 qubits if D-Wave already has 2,000 qubits, right? And they're already selling it, to customers. And, well, the issue is there's actually two issues, okay? First, there's sort of the engineering issue that, that these qubits just don't seem to maintain their quantum coherence very well, okay? They're sort of like, they're a technology that is optimized for, getting as many qubits as you can, as fast as you can, rather than for making the qubits as good as you can, okay? And, many of us were sort of doubtful that, that with qubits that are that noisy that you would see a speed up, that you could, even if there were one to be had. And the second issue is a more theoretical one. The issue is, well, you're trying, D-Wave's entire approach is based on trying to solve NP-complete problems. But as I mentioned, these problems seem pretty hard, okay? And, it's not clear that even if you could run this adiabatic algorithm perfectly, that you really would see much speed up for these problems. Okay, probably you can see a Grover type of speed up, a square root speed up. Maybe even that, is not certain, because you got to compare against classical algorithms that themselves are very clever and that could be much better than brute force, right? But are you going to see an exponential speed up? We don't know, right? So there was a hope about it that this adiabatic algorithm could take advantage of a phenomenon called quantum tunneling, which basically says, like, if I have if I'm trying to find the minimum in some potential, but I have a spike sort of along the way that's blocking me, well then where a classical particle might get stuck over here for exponential time, a quantum particle can actually get over the spike, in a much more efficiently in polynomial time, right? This is very important. This effect is central to why, the hydrogen atoms in the sun are able to fuse into helium, for example. Okay, they have to get over a barrier like that. Okay, but we could exploit that algorithmically. But then, when we're trying to solve real-world optimization problems, well, is the fitness landscape actually going to look like that? Well, who knows? And if it does look like that, maybe you could design a better classical algorithm, that would take advantage of it, right? So, so people studied this for a while, and what they found is that the amount of time that you have to run this adiabatic algorithm for, if I want to end with the solution to my NP-complete problem, is determined by something called the minimum eigenvalue gap of my Hamiltonian. Don't worry what those words mean, okay? Basically, I see, I have a graph with two things, and and I look at the closest that they ever get to each other, and however close they get, I need to run my algorithm for the inverse of that amount of time, Okay, and so then people say, Farhi and my other physicist friends looked at this and they said, well, why are they going to magically get super duper close to each other, right? And that's the only thing that would cause the algorithm to fail. Okay, but then people studied it on, they looked at it on hard instances of NP-complete problems, satisfiability, things like that, and lo and behold, they found that this gap does seem to become exponentially small, right? It was hard to tell from the numerics, and there was a big debate about it for a few years. Okay, but Farhi has told me the wonderful story that he once, went to an expert in condensed matter physics. Because, for their own reasons, they have decades of experience calculating these spectral gaps. Okay, and he asked, well, based on your experience with similar systems, do you think that, in our adiabatic algorithm, that this spectral gap will decrease polynomially or exponentially as a function of the number of particles? Okay, and this expert thought about it a bit, and he said, I think it will decrease exponentially. Okay, now that was not the answer that Farhi wanted to hear. So he said, why? What's the physical reason for it? Okay, and the expert thought about it some more, and he said, well, it's because otherwise your algorithm would work. Okay, so after you've seen enough examples of nature sort of just failing to solve NP-complete problems in polynomial time, you might be tempted to, just want to take that as a fundamental principle or, postulate alongside no superluminal signaling and the second law and so forth. And you might wonder, supposing I accepted that postulate, what else could I then use it to explain? Okay, so that's, that's a direction that interests me a lot. Okay, so, I'd say it remains unclear whether you really get a practical speed up this way over the best classical algorithms. We might not know for sure until we can really build quantum computers and test them out. All right, so a lot of my work, in the last, 6 years or so has been about this very unfortunately named goal of quantum supremacy, which basically just means getting a clear quantum speed up, not necessarily for something useful, but just for something hard. Okay, and so my student Alex Arkhipov and I had an early proposal for how to do that, which was called boson sampling. Okay, and what we suggested was like a very, very rudimentary type of quantum computer where you just generate a bunch of photons, you send them through a network of beam splitters, and then you measure where they end up. Okay, now what is that useful for? Well, I have no idea. Okay, but we were able to give evidence that you sample from some probability distribution where sampling from that distribution classically would be exponentially hard. Okay, and so people have actually started implementing this. So far, they've done it with about 6 photons. If you want to outperform a classical computer, you probably need at least like 40 photons or something. Okay, so that's a challenge. But in the meantime, I also mentioned this group at Google, which is planning very soon to have a 49-qubit chip. Now, as far as we can tell, a 49-qubit chip is probably still not useful for anything. Okay, but if we just put a bunch of quantum operations on that, and we use it to sample from some distribution over 49-bit strings, then we have pretty good reason to think that, well, that is a distribution that if you want to sample it with a classical computer, you'll need something like 2 to the 49 steps. It may be a little bit better, but that's about the best that we know. Okay, and so so it's not so hard that a classical computer can't do it, and that's important because you want the classical computer to be able to check the results, and we only know how to do that by using this exponential time operation. Okay, but it's hard enough that you could clearly see that this chip would be solving something faster than the fastest classical computer that we have on Earth. Okay, so I think that will be, if and when that's achieved, possibly within the next couple of years, that will be a real milestone for this field. Okay, now I had stuff about the firewalls and the black holes. Because I am out of time, what I suggest to do is to just go to my conclusion. You can see, look at these graphics that I made. okay? Uh, you know, I have a Schrodinger's cat, I've got a wormhole, all right? So what I suggest that I do is that I just go to my conclusion, and then, if anyone wants to ask me a question about firewalls or something, then I can tell you about it, okay? So my summary is that quantum computers are the most powerful kind of computer allowed by the currently known laws of physics. There is a realistic prospect of building them. What I like to say is that if you can build a quantum computer and it works, that's the conservative possibility, right? I mean, when people come to my blog, let's say, and they say, this can never be done. I say, well, in some sense, I hope you're right? Because that would be a revolution in physics, right? But I think for me, the number one application of building a quantum computer is actually just to prove those people wrong. Okay, all the other applications are just icing to me. Okay, but what we've seen is that even a quantum computer, contrary to what the popular articles say, is not this magic oracle that solves everything. Okay, even they have limits, and the limits are sort of so strange and sort of cut across things, in such a non-trivial way that I like to think no science fiction writer would have had the imagination to invent this, right? It's, people usually go wrong by trying to round it down to something that a science fiction writer could have thought of, okay? But, the limits of quantum computers have explanatory power. They can explain why spectral gaps behave the way they do, and in the part of the talk that I haven't gotten to, I could tell you why they might even help to protect the geometry of space-time. All right, so let me stop there for now. So thank you.
Scott, why do you say that these limits might help protect the geometry of space?
Oh, you really want to know? All right. All right. Anyone wants to leave, I won't be offended. All right? All right. All right. So now, all right, you've seen this guy. I sort of never, when I was here at Berkeley doing my thesis about quantum computing, I sort of never imagined that it was, it was going to have anything to do with black holes. Like, I just, read about them in, popular science, the same as anyone else, okay? There was a remarkable connection that's really been made within the last 5 years or so between quantum information and quantum gravity, okay? Including famously this black hole information puzzle. So this was a central problem in modern physics, which was raised by Hawking in the 70s. And it's basically, the rules of quantum mechanics are except for measurement, which let's just forget about measurement for now, okay? But if I just have a bunch of qubits and they're revolving on their own, then everything they do is time reversible, okay? So, I can run things backwards as well as forwards, and information is never destroyed, okay? But a black hole seems to violate that. Right? If I take some bits, or I take an encyclopedia or something, I throw it into a black hole, well then general relativity tells me it's gone, right? It's hitting the singularity, it's never getting out. Okay, so it seems the universe seems to have an information dumpster, okay? Which then the question is, how do we reconcile that with quantum mechanics? Okay, well, Hawking also famously, this is my animation, right? So Hawking also famously discovered in the 70s that black holes radiate. Okay, so they're not completely black. Actually, photons slowly come out. For a black hole the mass of the sun, it may take about 10 to the 67 years for this to happen, but eventually the black hole will go away. Okay, but the trouble is, his calculation also said that the radiation that comes out, it suggested it would be completely thermal, completely uncorrelated with whatever came in. So the puzzle remains. Okay, and there's a bunch of possibilities, none of them very appealing, right? If it stays there forever, we violate quantum mechanics. It comes out. okay, well, we can imagine that somehow, by some yet unknown physics, the information that's dropped in would come out in some scrambled form in the Hawking radiation. Okay, but then that leads to a problem as well. Because from the perspective of someone who is inside the black hole, well, the information doesn't come out, right? It just, hits the singularity and goes splat, okay? So now you seem to have two copies of the information. And well, why is that a problem? Well, it's because if I have a quantum state, then there's a basic principle of quantum mechanics called the no cloning theorem, right? Which says that there is no way to actually make a copy of an unknown quantum state. Okay, this is the central principle, by the way, that enables quantum cryptography and other possible applications, such as quantum money, which would be physically impossible to counterfeit. Okay, but I digress. That's a different talk. Okay, so then people in the 90s started developing a view called black hole complementarity, which says that actually, you should not even think of the interior of the black hole as being a different quantum state than what was, available to you outside of the black hole, including on its event horizon. Okay, you should just think of them as different re-encodings of the same quantum state. And then jumping into a black hole, is just a really weird way of measuring the same quantum information that you could have measured had you stayed outside the black hole. All right, well, that seemed to, sort of resolve the problems for a while. I was always confused about it. And then what happened in 2012 is that a bunch of physicists decided that they were confused about it too. Okay, and so then this led to a huge sort of discussion in theoretical physics, which even spilled into the New York Times, and so you may have seen something about it. It was called the firewall paradox. Okay, so what is this? It was by Almhiri, Maroff, Polchinski, and Sully in 2012. And this was sort of a challenge to this black hole complementarity. And so it was a thought experiment where, the idea is we would form a black hole. We would have complete knowledge of the entire quantum state of all the infalling matter. It's a thought experiment. Okay, and we let it form a black hole. Then we let the black hole mostly but not completely evaporate. Okay, which takes 10 to the 67 years or so. We'll assume we have a really good grant. Okay, and then as the Hawking radiation comes out, we route all of it into our quantum computer. Okay, we just treat it as a collection of qubits. We process it in a certain way, and then we make some measurement which will tell us that that a Hawking photon that's just now coming out of the black hole is entangled with all the photons that previously came out. Okay, and then we jump into the black hole. Okay, for the sake of science, and we look at what's happened, and now there's a principle of quantum mechanics called monogamy of entanglement that says that if I find a qubit and it was already entangled with a second qubit, then it can't also be entangled with a third qubit. Okay? But now there's more principles in quantum field theory that say as I fall into the black hole, here's Alice. It's always Alice for some reason. Okay, she jumps into the black hole. And now, because these two qubits were entangled, the qubit that's just now coming out of the black hole cannot also be entangled with a qubit that's just inside the black hole. Okay, but Hawking says if you want to see a smooth space-time at the event horizon, then you need that entanglement that straddles the event horizon, right? And it sounds crazy, but in quantum field theory, space-time is built up out of sort of a huge amount of local entanglement. If you don't have that entanglement, you've got no smooth space-time, which basically just means space and time end at the event horizon, okay? And Alice encounters, an end of space-time, which was called the firewall. Okay, now, why is that a problem? Well, Alice was supposed to encounter an end of space-time, but only at the singularity, right? And this is saying she would hit one much earlier, that she can't even cross the event horizon. Okay, so then the question is, what gives, right? And what what made this a big deal is that it's not just a philosophical problem, right? It's like if you claim to have an answer, then you have to say, well, if Alice did this, then what would happen? Okay, so there have been a whole bunch of suggested resolutions. There have been hundreds of papers about this paradox. Okay, but one of the maybe the most interesting things that's been said about it was said by Daniel Harlow and Patrick Hayden, and what they did is they said, well, yeah, it's true that black hole complementarity says that it implies that Alice could do some quantum computation on the Hawking radiation that would show her that there is this entanglement, and therefore create a breakdown of quantum field theory at the event horizon. Okay, but let's now ask, well, how hard of a computation would she have to do? Okay, and what they did is they argued that the computation seems like one that would be exponentially hard even for a quantum computer. Okay, so take time exponential in the number of Hawking photons that she's dealing with. Okay, so what do we mean there? We mean she can't do it in a mere 10 to the 67 years. She can't even make a dent in it in that time. She instead needs 2 to the 10 to the 67 years. Okay, so by the time that she had done this, the black hole would have already evaporated anyway. So maybe there's nothing to jump into. So maybe there's no problem. Okay, so that was that was kind of what they said, and now you can have your own view on how whether that satisfies you or not. But the thing that blew me away was that when they came to the crucial point, why is this an exponentially hard problem? They drew on sort of all the work that we had done over the last 20 years in understanding what are the limits of quantum computers. And in particular, their argument sort of relied usually on this thing that I did in my PhD thesis here at Berkeley, okay, which is the thing, the sort of best known thing that I showed in my PhD had to do with the ability of quantum computers to find collisions in something called cryptographic hash functions. Okay, so a hash function is like a function that maps some string to a much shorter string, and they're super useful in cryptography. But the key property that they're supposed to have is that it has to be intractable to find 2 different inputs that map to the same output. Okay, and so what I showed is basically that if I have just a hash function that's a complete black box, just like that setting that we talked about earlier with Grover's algorithm, then in that case, even a quantum computer will need exponentially many queries to find a collision in that hash function. Right? It turns out that if let's say my hash function has n possible outputs, then classically finding a collision takes about square root of n steps. Right? Why square root of n? Well, because of the birthday paradox. You've heard of that, right? It's if there's 23 people in a room, there's even odds that 2 of them share a birthday. Right? What matters is the number of pairs of people. Okay. Now it turns out that a quantum computer could find a collision in such a hash function using only cube root of n steps. I'm not making this up. Okay. You get cube root of n by sort of combining the birthday paradox with Grover's algorithm in a clever way. Okay, so what our work showed in 2002 is that actually even with a quantum computer, cube root of n is the best that you can do. Okay, now what Harlow and Hayden argued was that actually you can sort of take this collision problem, this finding collisions in a hash function, and you can embed it into the problem of decoding the Hawking radiation that is coming out of a black hole in such a way as to create a firewall. Okay, you can sort of reduce one to the other. Okay, so that if you had a generic efficient algorithm for decoding this Hawking radiation, then it would let you find collisions in hash functions, which we think is hard even for a quantum computer. Okay, so now recently I strengthened their result, show that performing this computation is actually doesn't is hard even without using my PhD thesis. Okay, so in fact, if you could do it, then you could invert what's called, basically any one-way function using a quantum computer, okay, which would let you break not just public key crypto systems like RSA and so forth, but even any private key crypto system, that's based on any mathematical assumption. Okay, so, so whether it solves the problem or not, the problem indeed seems to be hard, So, and what's happened in the last 5 years is that, computational complexity has been feeding back into fundamental physics in all sorts of ways. So I have a recent result, about, you've heard of the Schrodinger's cat experiment, right? And people wonder if if I maintain a cat in a superposition of alive and dead states, well, what does it mean? Do I have to talk about two universes that, are both somehow existing, which is the many worlds philosophy, okay? And what my result says is that if I had the technological ability to, make a Schrodinger cat and then measure it and confirm that it was in this superposed cat state, then I would necessarily also have the ability to bring a dead cat back to life. Okay, in the sense that the quantum circuit complexity of one task is basically the same as the size of the circuit that I would need for the other task. Okay, so so in the dead state, it's not clear we should even call the cat dead anyhow. I mean, it's it's alive, it's dead, it's alive, it's right. So I mean, so in fact, the Schrodinger's cat experiment involves way less animal cruelty than is normally supposed. Okay. Okay, and then the craziest one to me is that since about 4 years ago, there's been a whole bunch of people who call themselves string theorists, led by Lenny Susskind at Stanford, who now they don't talk about strings anymore. Okay, they are speaking in a language of qubits and quantum circuits and entanglement. And this is now what they talk about, okay? And a lot of the reason for that has to do with what's called the ADS-CFT correspondence, which is like one of the most important things to have come out of string theory, and it's sort of a holographic duality which relates physical theories in different numbers of dimensions. And this is sort of one of the best handles that anyone has on what a quantum theory of gravity can look like, okay? But the crazy thing that people found was that when you, I can take some situation involving general relativity, for example, a wormhole between two different regions of space, and general relativity says that a wormhole will just continue expanding forever, okay? It'll just get longer and longer, and in fact, the standard wormhole in relativity is not traversable, right? I go in it, I can't get out the other end, because it's, so now, what else do we know that's sort of somehow a connection between two things and yet doesn't let you send a signal from one to the other? Well, quantum entanglement, okay? And so what's become increasingly clear is that these two things are extremely related to each other. In particular, when you take these holographic dualities, if I take a wormhole and I look at what it corresponds to, on this boundary theory, this quantum field theory that lives on the boundary, then I find an entangled quantum state. Okay, and as the wormhole gets longer and longer, the only thing that is changing about that quantum state that would sort of track the length of the wormhole seems to be that this quantum state gets more and more and more complicated. Okay, but what do you mean complicated? How can you quantify it? Well, Suskind's proposal is that what we mean is literally the quantum circuit complexity of that state, meaning the number of operations that I would need to prepare that state using a quantum computer. Okay, so because of this connection, circuit complexity has now started sort of playing the role of a fundamental quantity in physics, at least in the context of ADS-CFT. So I don't know where all of this is going, but I sort of have no choice but to when they come to me as what do I know about wormholes or black holes, okay? But if they want me to use me as a computer science consultant, and they can boil down their question to something about quantum computing, well, we're here to serve. Okay. All right. So thank you for asking. That was the answer to your question.